Welcome back. In this lecture I shall discuss various methods of producing low temperatures. The specific objectives of this particular lesson are to discuss methods of producing low temperatures using first sensible cooling, using endothermic mixing, using phase change processes, using expansion of liquids, expansion of gases, thermoelectric methods, and finally magnetic methods. At the end of the lecture you should be able to list various methods of producing low temperatures, explain the salient features of these methods, and explain the process of isentropic and isenthalpic expansion of liquids and gases and the practical significance of these methods. Let me give a brief introduction. First of all, let us look at the definition of refrigeration. If you remember, refrigeration is defined as the process of cooling of bodies or fluids to temperatures lower than those available in the surroundings at a particular time and space. Okay, that means the temperature of the system which is being refrigerated should be lower than the surrounding temperature. That is the major point to be noted here. Okay. And to achieve refrigeration, it is essential to produce temperatures low enough for heat transfer to take place from the system being refrigerated to the system producing refrigeration. So let me explain this. Okay, let me draw the temperature axis here. Let us say that this is your temperature axis, and let this be the surrounding temperature, T surroundings. Let us say that we have a cold storage. Okay, this is a cold storage which is initially at the surrounding temperatures. Now we would like to reduce the temperature of this cold storage to a required level. Let us say that this is your required temperature. So the cold storage temperature has to be brought down from the surrounding temperature to this temperature. Okay, temperature is increasing in this direction. How this can be done? In order to do this, what is required is there should be heat transfer from the cold storage so that its temperature can reduce. Okay, so as you know very well, for heat transfer to take place, we must have another system which is in thermal contact with this cold storage and whose temperature is lower than the final required cold storage temperatures. Okay, that means let us say that we have a refrigeration system, okay, whose temperature T ref is less than the final cold storage temperature T required. Okay, so this is a, let us say that a cyclic device. If I bring this cyclic device in thermal contact with this cold storage, then there will be heat transfer from the cold storage to this refrigeration system. As a result, the temperature of the cold storage drops, and if the system is designed properly, the cold storage may finally settle at the required temperature. Okay, so this is our final required cold storage temperature. Okay, now it is not enough that you just reduce the temperature of the cold storage to a required level. You also have to provide refrigeration continuously. Okay, that means refrigeration system is required first to reduce the temperature of a cold storage from that of the surrounding to that of the required temperature, and you also have to maintain the cold storage at that particular temperature. Okay, what do we mean by maintaining? We know very well that we don't have any perfect insulation in nature. Okay, and the moment you bring this cold storage temperature lower than the surroundings, there will be heat transfer from the surrounding to the cold storage. Okay, some heat transfer continuously takes place from the surrounding to the cold storage. If you do not do anything, then the cold storage temperature starts increasing. Okay, so if you want to maintain the cold storage at this required temperature, you must take out heat from the cold storage at the rate at which it is entering or at the rate at which it is being generated inside the cold storage. That means there must be continuous heat transfer from the cold storage to the refrigeration system. Okay, so this is Q out. Okay, that means heat transfer takes place from the surrounding to the cold storage because of this delta T, and this has to be taken care by extracting heat from the cold storage using a refrigeration system. Again, there should be some delta T temperature difference is required so that this heat transfer can take place. Okay, so finally the heat is coming to the refrigeration system, and if it is a cyclic device, whatever heat is coming to the refrigeration system must be thrown somewhere else. Okay, we will see that how it will be finally rejected. Okay, but what is important here is that we must be able to produce low temperatures using a refrigeration system. That means this temperature, okay, a low temperature or refrigeration temperature, such that the cold storage can be maintained at the required temperature. Okay, so this is an example of a cold storage. But any refrigerated space, for example an air conditioned space or a domestic refrigerator or anything, okay, what it involves is to produce low temperatures so that heat transfer can take place from the space that is being refrigerated to the system which is doing the refrigeration. Okay, and inside the refrigerant system we must be able to achieve low temperatures. Okay, so the topic of this today's lesson is how we can achieve these low temperatures. Okay, so let us look at some of the methods of achieving low temperatures. The various methods of producing low temperatures are sensible cooling using a cold medium, endothermic mixing of substances, phase change processes, expansion of liquids, expansion of gases, thermoelectric method and magnetic method. First let us look at the sensible cooling method. So producing low temperatures using sensible cooling using a cold medium. If a substance, let us say system A, is available at a temperature lower than the required refrigeration temperature, then by bringing it in thermal contact with the system to be refrigerated, that means system B, the temperature of the system B can be reduced. Okay, let me give an example again. Let us say that we have a building. Okay, we would like to reduce the temperature of the building, and at our disposal, let us say that we have a large body of cold water, okay, whose temperature is much lower than the surroundings, and I want to cool the building which is initially at the surrounding temperature. So when I bring the building in thermal contact with this cold water whose temperature is lower than the surroundings, heat transfer takes place from the building to the cold water, and in this process the temperature of the building reduces below that of the surroundings. That means I am able to produce refrigeration, okay, because I am reducing the temperature of the system to a level lower than the surroundings. Okay, so how this is happening? This is happening because of the sensible heat transfer between the building and the cold water. Okay, I have, as I said, I have cold water at my disposal, so this is possible. And what happens to cold water during this process? During this process, the cold water temperature has to increase. Okay, if it has a finite thermal capacity, since it when it absorbs heat, its temperature increases. That means during the sensible heat transfer process, the temperature of the building reduces and the temperature of the cold water increases. Okay, so this is one of the simplest methods of reducing the temperature of a system. Okay, of course, for this to happen continuously, we must have a continuous supply of the cold water so that you can continuously provide the refrigeration. Okay, another example is use of cold air for reducing the temperature of air in a conditioned space. Okay, if you want to reduce the temperature of air in a conditioned space, you can supply cold air which gets mixed with the warm air inside the room and the temperature reduces. Okay, so here there are no latent processes, all the processes are sensible heat transfer processes. Okay. In the absence of heat losses, the heat transfer during this process, if let us say that over a time period, if Q is the heat transferred during this process, then Q can be written as Q is equal to MC into TF minus TI of A, that is equal to MC into TI minus TF of B. Okay, here A is a system that is providing refrigeration. That means in this example, A is the cold water and B is the building, okay, whose temperature is getting reduced. So the heat transferred from the building in the absence of any losses will be exactly equal to the heat transferred to the cold water. Okay, and from this equation, if you know the thermal capacities of the building and cold water and their initial temperatures, and if I assume that the complete system, that means the building and the cold water attain an equilibrium, then you can find out what is the final equilibrium temperature. Okay, and as I said, in this equation, Ti and Tf are the initial and final temperatures, M is the mass and C is the average specific heat of the system. Okay, so this is one simple way of producing low temperatures using a cold medium. Now let us look at the second method. Second method is producing low temperatures using endothermic mixing of substances. This is in fact one of the oldest methods known to mankind. And we know that, for example, from experience, let us say that you take a glass of water and if you add glucose to it or sugar, okay, then we know that if you add sufficient amount of glucose or sugar, the temperature of the water reduces, okay. Now that means the water temperature at the end of mixing will be lower than that of the surroundings, okay. Why this is happening? This is happening because mixing of glucose in water is an endothermic process. Endothermic process means heat has got to be supplied during this mixing process, okay. So this heat is supplied from the water itself. As a result, water temperature drops, okay. So as I said, mixing of certain substances produces very low temperatures due to the endothermic nature of the mixing process. And if you want very low temperatures, of course we have to use certain specific materials. For example, if you are dissolving sodium chloride salt in water, then you can achieve a low temperature as low as minus 21 degrees centigrade. And if you are dissolving calcium chloride salt in water, then you can get a temperature as low as minus 51 degrees centigrade. Okay, so this is one of the simplest ways of producing very low temperatures. But this method is not very practical as far as a practical refrigerant system is concerned, because it suffers from certain disadvantages. What are those disadvantages? The first disadvantage is that the refrigeration effect produced by endothermic mixing is typically small. Okay. So you cannot have very high capacity using this method. And second problem is that recovery of salt for reuse is very difficult. Okay, that means if you want to provide refrigeration continuously using this method, you have to have an infinite amount of salt at your disposal and an infinite amount of water at your disposal. Okay, which is not, which as you know is not possible. And if you want to recycle the same salt, then you have to separate the salt from the solution. Okay, which is very difficult. Right. So because of these two limitations, this particular method is not used in practical continuous refrigeration systems. Okay. Now let us look at the third method. Third method is the use of phase change processes. We know that low temperatures can be produced using substances that undergo endothermic phase change processes such as sublimation, melting and evaporation. Okay, so as you know very well, phase change means there will be a change of phase from either solid to liquid or solid to vapor or liquid to vapor. Okay, and these phase change processes, that means solid to liquid, solid to vapor and liquid to vapor, are endothermic in nature. Okay, that means heat has got to be supplied to the system undergoing these phase change processes. Okay, so during this process a large amount of heat can be transferred, right. Let me give some examples. For example, the latent heat transfer. Let us look at the amount of heat transfer during this process. For example, if I am melting water ice at 0 degree centigrade, then I can get a heat transfer rate of, or heat transfer of about 335 kilojoules per kg of ice. That means when 1 kg of ice melts at 0 degree centigrade, 335 kilojoules of heat is transferred. And the second example is sublimation of carbon dioxide at minus 78.5 degrees centigrade. When dry ice or solid carbon dioxide sublimates at this temperature, 573 kilojoule of heat is transferred per kg of solid carbon dioxide sublimated. And the last example is vaporization of ammonia at minus 20 degrees centigrade. That means when liquid ammonia vaporizes into gas at minus 20 degrees centigrade, 1330 kilojoule of heat is transferred per kg of ammonia vaporized. Okay, so these are typical examples and the typical temperatures. So one thing you can notice here is that unlike compared to the sensible heat transfer processes, here per kg of substance a large amount of heat can be transferred. Okay, so this is one of the advantages of this particular method. In addition to that, when we are using pure substances for phase change, the temperature remains constant during the phase change process. You know very well that water boils as long as you keep the temperature constant. Pure substance always boil or always condense at the same temperature. That means the heat transfer process is isothermal in nature. Okay, so this is another advantage of the phase change process. Okay. Now, so let us look at this method. First of all, both water ice and dry ice are widely used to provide refrigeration in several applications. Okay, we know that in many common this thing we use ice for producing refrigeration. For example, if you want to have cold water quickly, Okay, you can add ice blocks to water. Okay, so that is the quickest way of reducing the temperature. And these methods are also used in some special applications such as transport refrigeration. Okay, especially solid carbon dioxide is used very widely in transport applications to keep the products cool. Okay, when you are using solid carbon dioxide, you can achieve temperatures as low as -78.5 degrees. So that means you can use this even for frozen food storage. Okay, so these refrigerant systems, that means there are systems which use ice or solid carbon dioxide, are known as expandable refrigerant system, because at the end of the process, normally the water or carbon dioxide gas is not recovered. That means the refrigerant gets expanded. Okay. Now, however, in actual systems, we do not really rely on solid ice or solid gas processes, but we use liquid vapor phase change processes, that means evaporation. Okay, why? Because evaporation is the most commonly used phase change process, because it is easier to handle fluids in cyclic devices. Okay, if you can, as you know, most of the common refrigerant systems are cyclic in nature. Okay, so in cyclic systems, it is much easier to handle a liquid or vapor rather than a solid. Okay, because transporting the solid around the cycle is difficult. Okay, so for this reason, in most of the systems we use evaporation and condensation. Okay. So for all phase change processes, the amount of refrigeration produced is given by Q is equal to m into delta H subscript pH, where Q is the heat transferred during the process, m is the amount of substance that has undergone phase change, and delta H pH is enthalpy change during the phase change. Okay. Apart from the latent heat, the temperature at which the phase change occurs is also important. Okay, because ultimately we have to produce low temperatures. Okay, so the amount of heat that is transferred is important. In addition to that, the temperature at which heat is being transferred is very, very important. Okay, and for liquid to vapor phase change, the normal boiling point is a good indication of the usefulness of a particular fluid for refrigeration applications. As you know very well, a normal boiling point is the saturation temperature at 1 atmosphere pressure. Okay, this is a good indication of the usefulness of any fluid for refrigeration purposes. Okay, for example, water has a normal boiling point of 100 degrees centigrade. That means at 1 atmosphere its temperature is 100 degrees centigrade, which is way beyond the surrounding temperatures. So if you want to use water as a refrigerant, then you have to reduce the pressure. Okay, that means if a refrigerant system uses water, then it will be operating at pressures very much below the atmospheric pressure. Okay, so this is how the normal boiling point will tell you about the operating pressures. Now, the latent heat of vaporization and normal boiling point are related by what is known as a Troughton's rule. The Troughton rule says that delta SFG. Okay. Delta SFG is nothing but the molar entropy of vaporization is constant for all fluids. That is what the Troughton rule is all about. Constant means not a single value, but it is found that this value for most of the fluids lies in this range. Okay, and what is this delta SFG? Using your thermodynamic relations, we can write delta SFG as delta HFG divided by TB, where TB is a normal boiling point and delta HFG is a molar enthalpy of vaporization at normal boiling point. Okay, so the Troughton rule says that the ratio of the molar latent heat of vaporization at normal boiling point divided by the normal boiling point in Kelvin is constant for most of the fluids. This rule is very interesting, and it is also very useful because you can derive certain things from this rule. For example, from this Troughton's rule, you can see that the latent heat of vaporization increases as the normal boiling point increases. That means as TB increases, delta HFG increases. And you can also find from this equation that substances having lower molecular weight will give rise to higher specific latent heat of vaporization. Okay, that means on per kg basis, the latent heat of vaporization increases as the molecular weight reduces. Okay, in fact you can just compare, for example, water has a molecular weight of about 18, and you compare this with any refrigerant whose molecular weight is much higher than the water, and you will find that at normal boiling point the latent heat of water is much higher than latent heat of any other refrigerant with a higher molecular weight. Okay. Now, a refrigerant, as I said, should have low normal boiling point so that they vaporize at sufficiently low temperatures. Okay, as I said, if you want to have produce low temperatures at reasonably high pressures, then the normal boiling point should be low. However, if the normal boiling point is very low, then the operating pressures will become very high. Okay, that means a normal boiling point should lie within a certain range for the fluid to be useful in a refrigeration system. And the Clausius-Clapeyron equation relates the vapor pressures with temperatures, and it is given, you must have studied this in your thermodynamics, the Clausius-Clapeyron equation. This is given by